Okay, let's get started. Everybody can hand to the side of your person, and I'll give you guys some feedback on the questions. And two more. Everybody should feel very good about this, right? Are you the only one? Then I can find you.
I don't think I put my name on it.
Oh, both of you?
I don't.
Okay. Can you write your name? Okay, let's get started. So everybody should feel pretty good about this test, right? Quiz? Relatively easy. Actually, that's some of the most fundamental concepts of the class. We talk about chain confirmation. So the last class we talked about something quite unique. Something we talked about is radius of gyration. We actually understand how now we can measure your chain dimension. Not just by something on the board in terms of end-to-end distance. We now have a value to understand how big your polymer is. So we understand how the link between the end-to-end distance and the radius of gyration, right, everybody? So you're going to encounter this radius gyration term quite a lot in next year, where you're studying the light scattering technique, as well as GPC, any techniques. They basically measure how big these polymer chains are, and you will use these techniques to link to your molecular weight, etc. So what are we going to do today? Anybody can give me some advice? What are we going to do today? We have 3 sections left. We have 6.6. In textbook it's called rod, coil, and maybe globular. Okay, globular, which is compact size. It's very easy to explain those concepts. Then we're going to talk about 6.7 as well. The 6.7 is about distribution of chain and distance, okay? And that will be the main focus of today's class. And last one is we're going to touch base about what's the real chain behave in solution. Okay, so let's get started. Since the other two sections will be relatively similar, so I will combine those two and discuss at the end. So we're going to start with chapter 6.7 for this class. And specifically about chapter 6.7 is talk about statistics about chain confirmation. How's everybody's feeling about reading chapter 6.7? Have everybody had a chance to take a look? It's quite intensive in terms of equations, right? So as usual, we're going to leave that to the end. We're going to start talking about why we should care about that particular chapter. So think back to the first few class. What we talked about is end-to-end distance, chain dimension. If you might recall, we always had discussed the average, right? Everything we talked about is the average. Average end-to-end distance, average radius of gyration. So I'm going to ask, hey, Erdig, would you mind actually mute the volume, because it's from time to time actually make a lot of noise from outside. Okay. Appreciate that. If you have a question, feel free to turn it on and ask. Okay? Okay, no, much better. Feeling a different more. So, chain statistic and non-time average, it's very critical. in some applications, because not every time you will need to consider average. What if you just don't want to freeze a given moment and just look at probability of what end-to-end distance is? So everybody knows by now end-to-end distance should be equals to mb squared, right? You have to know it by now. And this average means if you consider one given polymer chain, on the board it looks like static, right? But on real, for given molecular weight, we talk about different chain conformation. They would cause billions and billions of different chain conformation. So you would have different end-to-end distance for given chain conformation. Okay, does that make sense to everybody? I can say maybe the same chain can adopt this. Or maybe they will be relatively compact. So your H will depends on what the time point of your looking at molecular and what is the condition of your molecular. In particular case, the polymer, right? And the first 3 chapters, we always talk about statistical average. So what we consider is always the final outcome of what has been averaged out for all the molecular. So for today's class, we're going to actually dive into how about we don't give an average. Instead of, we want to look at what's the probability. What's the chance of finding at this state, or this state, or this state? In other words, I know computer science is very powerful these days. If they can actually do motion recognition, they can probably tell Dr. Gu's probability of standing straight with hands down versus this. It will not be the same probability. And as you can guess, which one will have a higher probability? If we say P will be state A higher, or probability of state B? Given a number, let's assume this h squared is exactly at mb squared, and this will be 10 times mb squared. Let's call it no longer have the average. Okay. Which one would have higher chance? A, right? But doesn't mean we wouldn't have any chance to have B. So probability definitely will be higher. And there's another way you can actually understand this. H average equals to mb squared is averaged probability in terms of end-to-end distance. Okay? So let's follow the line. So the first part of the class, we're going to introduce concept of probability. Okay, we're going to discuss in the simplest case in one-dimensional polymer chain again. So we're going to go back in terms of time. Going back to the first 2 lectures we talked about in terms of random walk, we're going to discuss how does random walk help us understand the probability of where you find the end of your chain position versus where you're beginning from. Okay, so we're going to use that example, then discuss what if it's a 3-dimensional random walk. What's the probability you find your particular polymer chain at a given location? Okay, we talk about non-time averaged, and please pay attention to this particular words. We're not going to look at time averaged anymore in this class. We're going to look at specific state, okay? So, well, let's consider one-dimensional random walk. We talked about in the first class. Let me turn the laser projector off. We don't need it for now. We will come back to it. Let's consider a random walk again. So what we are drawing is number of steps. Okay? This is the number of steps you're going to go. Each step you have tend to go positive or negative. So in other words, you would absolutely start from 0, and if you take one step, you can go either forward or backward. If I draw another table here, we're going to call it, this would be 1, 2, 3, 4 in terms of axis, y-axis, okay? And if you take 1, 2, 3, 5 different steps. So let's assume you have the equal chance to take a positive one or move forward, basically say, and negative one in other words, if I and the imaginary polymer chain, if I could go around, I can either have 50% of chance go forward or 50% chance go negative direction. So if I take one step, what's the final location I could be ended up, and what's the probability for each?
+1, -1, 50-50.
Exactly, right? So we would have ended up let's just compile a table. If I take one step, I'm going to have (50-50) chance to end it up at either. This is one step, right? And each of them are 50-50 chance. If I take two steps, now I standing at 0, what is possible state? How many states would we have? If I take 4, right? It's going to be total of 4, right? Where does the 4 come from? Because either for each step, I could either take a positive one or negative one. So I potentially could end it up. Is it possible I end it at 1 if I take 2 steps?
Oh, no.
Yeah, so I wouldn't be able to end it up at 1 because I need to take 2 steps. For one step, I could be either at +1 or -1. So how about I take 2 positive steps? I would end it up at x equals 2. If I take 1 step forward, 1 step backwards, I would be ended up 0. And what's the other 2 state?
-2.
And and 0 again, right? You have two ways you can reach to 0. And this is important. You have two possible routes to reach to step 0. Okay? So we're going to do 2 more games, then we will stop there. How about 3 step? How many total state? It should be 2 power of 3 times, so total of should be 8 different states, right? Yeah, Sony?
So each different number of our, or not number of our steps, each round, kind
Yeah.
of, right? You're saying that each round it exponentially increases how many potential locations we have
Right.
from our starting point?
No. We always start from starting point. So think about I and the person who start from 0. Every time throw a coin. If it's positive side, I move forward. If negative, I move back. So if I say n equals to 3 steps, means I need to throw it 3 times. Okay? So now, with n step goes up, you have dramatic increase of number of chances. So how about now? I take 3 steps, where I could have ended up. 3? How many opportunities I can end up in 3? 1. I have to always throw a positive, throw a coin is always heads, so I can always take 3 steps forward. And I can take a negative 3, which should be symmetric. So how about in the middle? Am I possible here? No? Here? 3 times. Here? 0? Okay, can someone explain how we can count to this 3? And is there some rules we can follow to calculate? Yeah.
There's a pattern where every other step there's no possibility of being in that position.
Yeah.
And the internal steps are always the ones that are more equal to your possibility. Like, so 3 and then 2 and then 1.
Okay. So you're saying this is actually equal to the here, right?
Maybe.
It's actually, you are right for this particular step. So how about, let's do one last calculation. With it getting more complicated, how about 4? So we actually need an x equals to 4 and add one more row, x minus 4. This would be 0. How about here?
4. Oh no, that would be 2.
2. Explain how we get 2.
I don't know. My instinct just felt that. I don't have any sort of good justification for why I said it out loud.
Let's see. If I take 4 steps, I need to reach 2. I can easily see there's several possibilities. I can take 1 step, 2 steps, 3 steps forward, and come back, right? Or I can take 1 step forward, take 1 step back, then move 2 steps forward. Or I can easily do is take 1 step back, then take 3 steps forward. So this actually will be 4. And this will be, and this. Everybody is very good at this game. So what if I say I take n steps? What's the chance I end up in box random number x? X will have to be within 1, larger than minus 1, right? So we just play the game where we took 4 steps and have the chance we ended up in, for example, 2. Right? So what would be the generic way you can understand? So this relates to, in statistics, something called factorial. Okay? Then we're just going to talk about that in a second. But this gives you the chance of statistics. So this total number of possibilities is always equals to 2 to the power of n. Okay? So this will be equals to, there's 2 possible end state. Right? We can write a total state or total possibility, whatever you want to call it. It would be 2 to the power of n. When n equals to 1, you have 1. N equals to 2, you have 1, 2, 1. It's going to be 4. And this 1, 3, 3, 1, this is going to be total state of 8. And this is going to be 16. If you like to do the math, you can do it. So for n step, you always have 2 to the power of n possibility, right? Now the question is, how can you end up a number x? How many possible ways you can end up and number x? Should I give you some hint?
Permutation.
Hmm?
You have to use a permutation.
How do you do that?
Isn't it n choose x times the probability?
And say that again?
N choose x times the probability of n.
How,
Probability of x.
how do you, yeah, what is n chooses x?
So n factorial over n minus x factorial?
N factorial and n minus x factorial multiply. Did we miss something? Very yeah,
That's an x factorial.
yeah, right here. So what does this mean? Or we think about the other way to explain. To reach step x, does it care if I took the positive step at first or negative step first? It doesn't, right? Use this as an example. If I want to end up at x equals to 2, and we have total number of 4, as long as I take 3 steps forward, 1 step backwards, it's always going to be 2, no matter when I take that backward step. Okay? Listening one more time. If I want to be ended up at position 2, it doesn't matter which step I take first, as long as I take 3 steps forward, 1 step back. You're always going to add 2, right? 3 steps forward, 1 step backwards, I always going to end it there. So, same, let's just to do one gain. If I say I'm going to take 7 steps, to finish at 1. So to finish at 1, you need a 4 step forward. And 1 step, 3 steps backward. And no matter how you combine these two together, that doesn't matter. Okay? It doesn't matter either you take 3 at the beginning or 3 at the end or randomly mix in between. So total possibility, total ways you can reach 7 step forward or any 7 step is basically 7 factorial divided by 4 and multiplied by 3. That's the total number of ways you can be ended up at number 1 if you take 7 steps. And about possibility. What is possibility? Possibility is about chance. Okay? So we need to have P would equals total number of possible states with number of states to reach your goal. Okay? If we go back, what we should do just is 1 divided by 2. That's your 50% chance to end up either +1 or -1. If you take 3 steps, you have total of 8 different states, or possible states. And if the chances you end x equal to 3 is 1 divided by 8. Right? So if you do the math, this is about 12.5%. This is 37.5%. Same 37.5%. So you have more chances to end it up way closer to where it started off. That kind of makes sense. If you take 4 steps, the chances you ended up at where you start off is 6 divided by 16, 37%. And where if you ended up at number 4, which is 1 divided by 16, it's almost 6.25%. Very low, okay? And we can think along this as a one-dimensional random walk for our polymer chain. And if you apply this P for where as a random walk, where you would end it up is just going to be total number of states divided by like one of your classmates suggests. That's a possibility, P. Okay? So we're going to skip quite some math, but if you go back to the textbook, if you take a line possibility, you can simplify this just to 2x minus 2x squared divided by 2mb squared. The chances of you find a chain in the lateral dimension in terms with respect to the end-to-end distance. Okay, so let's say we have a polymer chain has n segments. Each segment length is b squared. What is the chance of we find the end of the polymer chain at position x? X is where a random, it could be any location along the polymer axis, okay? So with a little bit of rearrange, we know it will be proportional to exp to x squared divided by 2mb squared. I'll explain just in a second what these physical meaning of that. So if you look at this, when x is equal to 0, this would be the maximum of your probability. Same like here, if you add everything together, you always have more probability in finding anything in the center, right? Or where its origin coming from. So if we plot probability versus x, or location. Think about this as a random walk case. The chances where you ended up at where you start off is higher, much higher than the other chance. We talked about if we take 4 steps, this is about 37%. This is about 6%. This is about 24%. And as the chain goes longer and longer, this will be smoothed out to be a Gaussian function. And it will die out to 0 at some point. And this x is basically distance where you start off. So now if I pull a polymer chain, like I show here, if I just worry about vector from 0 to where my end states, there's some chances actually you found there will be come up to where they're starting off, right? This is the highest probability. And as your chain goes to be, the end-to-end distance gets longer and longer, the probability is lower and lower. Okay?
Could you say that one more time?
The probability to find a chain end far away from the origin of your axis is lower and lower. Okay? So for any given state, you would have different polymer chain adopting different states, but they follow this statistic of probability where you can find the end of your polymer chain is, either to be close or to be far away.
Somewhere in the middle.
Say that again.
Somewhere in the middle.
So probability here is just the distance to the center. But if you want to say find a probability to the center of your polymer, it's different. Okay? So can anyone suggest me what the difference would be? And how we can kind of use this probability to understand what is average end-to-end distance? Because you can just calculate out average end-to-end distance based on probability, right? If it's more probable, given distance, you can get what the end-to-end distance is.
Here, x and minus x are the same thing.
Yeah, x and minus x is the same thing, so it doesn't matter. So if you go to the textbook in Technology's book, what they plot is probability as absolute of x, because these are symmetric, so you can just take something off. Okay? We also should talk about not just the distance, but the chances of found a polymer segment at a certain distance from the center. Okay, this is a little bit hard to interpret at the beginning, but let me explain what that is. What is now the probability you find my polymer chain at a distance about h to the center of origin? How do we understand that problem? We have a 3-dimensional axis, x, y, and z. So x, y, you have a chain coming off, right? We talked about end-to-end distance, but how about if I say I want to find at a given distance h, just in a h, in terms a 3-dimensional h. If I draw h, it would be a spherical ball with the radius of h. we now not confined to necessary end-to-end distance, just a question about, in general, what are the chances of you finding it within that particular spherical domain. Now it's different because the distance to the center varies with how short or how far away. Because what is the surface area about a spherical? No, we just asking generally if you have a round ball, what is the surface area for a ball with R? Right? So surface area A, that would be related to the how much the surface area of that. Why this matters? Because think about when we come back to this topic, when we consider the distance to the origin, the surface area, or what is the distance to the center, changes over the distance r. If we want to have something really close to the origin, your probability of having a chain there is higher, but your shape of your ball is also lower, the surface area. Because when we talk about radius, it's smaller. Now you think about radius keep going out to the center, you have more surface area, right? If you think about two scenarios where we consider a spherical ball of this intersecting only this part, let me just use another color, that's better. Okay? So when you consider two cases, another radius is smaller. Although your chances to find the chain is higher, as stated by this probability function, right? The chances of finding a chain end is much higher at closer to the origin, but your spherical area is smaller. So if we want to consider a second term, which is probability multiplied by 4 pi area, just call it general h squared. And if you plot this as a function of probability and distance, what would be the change you can expect? Probability multiplied by 4 pi h squared. H is just the distance, right? We know h squared is proportional to what the distance to the center, right? So if you consider again the function of h squared, it will increase versus distance from center. How about this p? P in terms of probability will drop over the distance. So when you convolute these two effects together, if you plot p multiplied by 4 pi h squared, you actually would find a highest chance of you find a chain end. Okay? Now let me give you some real number. If we now take n equals to 1,000 step, now you would have a chance to find highest probability of having finding your polymer chain at the distance about 33 to the center. Okay? Everybody following why we come to this 33? it's a root square of 1,000. Everybody recall what is what it would be average end-to-end distance square equals to? It will be mb squared, right? So if n is equal to 1,000, your average end-to-end distance will be peaked at similar value here. Okay? And we can also calculate what's the chances of you finding it. You have 3% to find it at here. And this drops dramatically with increase of h. So if you just look at this particular curve, what you can learn is what are the chances if I find a second, if I tie the one end, what's the end at the distance from the center. If it's really close to the center, your chance of finding it is low because there's not much polymer chain. If I look at here, if I say I want to go in this circle, the chances of finding a polymer chain is just itself at here, right? When the chain is starting off, you have a probability of finding it. But with the distance n goes up, now if I go along this red circle, I can find here, 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 more polymer chain. The chances of finding my polymer chain itself is much higher. That's why you have increase in the probability. Now if I have one more color, let me change another color. There's not a lot of chance I can use. How about now? My circle is big, so my searching area on the surface of this is large. But there's not much chain going to extend that far. So if you have, although you have a large surface area, as implied by 4 pi h squared, multiplied by the probability is low, you would have a low number as well. Okay? So this tells you the statistic of the polymer chain. So the other take-home message you can have is the probability function. The probability of your polymer take n step ended up at h. N is n step of your polymer. H is what the chance you find in the distance of h. H here doesn't specifically mean end-to-end distance, okay? Just any distance. Would it be equals to a constant per factor, 2 pi multiplied by mb squared power of 2/3 multiplied by exponent minus 2mb squared multiplied by 3h squared. Okay? Okay, let's take a look at this mass equation, because not everybody is familiar with this particular mass equation. This is a constant. If you know what the n is, b is just a segmental length, right? If you know how long your polymer chain is, this is a constant. Won't change your probability. And the whole reason we have this is it will normalize that when you integrate from here to here, your probability will be equal to 1. Without this prefactor, if you just integrate this part, it won't be, probability will be equal to 1. So it's just a normalization function to help you achieve that. All right? But you will see, there's one thing I do want to point out is M-player rule here. if your chain goes longer and longer, your probability curve gets more flat. Okay? So look like this, even look like this. When n goes from, let's say, 100 to 1,000 to 10,000. Okay? So it will go flat because n contributed to normalization of your curve. But more important is the second part. This is the same probability function we talk about when you find the eponymous distribution from center, right? And please pay attention to this minus sign. That means when your distance goes up, the exponential drops dramatically. So this contributes to this p distribution function. So one last thing I'm just going to talk about, but won't require you guys to understand the math to derive it, is we actually can calculate end-to-end distance square. If we know the probability, then you can just average out the probability to get what is end-to-end distance, right? So before I just talk about that, any question about previously what we have discussed? Lena, please.
So I was just curious about how in the equation it says you have h and it says p parentheses n h, and you said that h was not end-to-end distance?
So this is average end-to-end distance. This h just means at any given distance. If this confuses you, we can replace with any value.
What is any distance? Is it
Any distance,
from the point to your
yeah.
Is it r?
yeah.
Okay.
It just be any distance from the origin to the end.
Got it.
So we also call it, because this is the basic tell you the average. You know, if you have a polymer, you have a million of different chains in solution, and if you just dissolve it and think about that, if you think along every human being sort of unique chain to these polymer chain, they will adopt different conformation. You could take a picture of each individual one and understand them, and they would have a distribution like statistic. So this basically tells you a generalization of your chances of finding your polymer, one polymer chain at a given moment, what they would adopt. I erased almost everything, but this basically tells you, and the chances you find end of it, not the polymer chain, just the end of it, okay? You find the end of your polymer chain will be highest where you start off. It's like a random walk. We just did example. If I move backward and forward and backward at equal chance, no matter how many steps I move, I would always end up where I start off. Right? Same for polymer chain. Even it's three-dimensional random walk going around, the end where you start from and where you end from is always going to be close. That's why this is probability. We only talk about the endpoints of the polymer chain. Okay? And we also did one more function I already erased. It's basically, let me actually erase the side next to it. Now, the probability not find the chain end, just to find the polymer itself, will follows 4 pi h squared. So this is just probability because 4 pi h squared is just a spherical face. You can find a polymer chain. Now have a peak. Because at the origin of it, what I just said is you have a high chance to find your chain, but your R is small. You know, there's not contained a lot of surface area you can search. But with the R goes on, your probability drops, but your search area 4 pi r squared is higher, right? Does this make sense to everybody? This is one of the important concepts.
So what's the x-axis there? That's just distance.
Yeah, this is just the distance again. Distance, you can just call it h. Okay, saying here will be distance h. So those has been covered quite extensively in the textbook, both. Okay.
So this will be like important for like a light scattering experiment on like what area the polymer you image or any sort of imaging.
No. It's not related to the light scattering at all, but for the completion of understanding the chain conformation,
Okay.
we have to discuss, not just talk about average, because what we did in the first 4 classes is always average end-to-end distance. So today's lecture is more about given one single moment, what's the chance of you see the polymer take. So
It's about the distance.
yeah, so if you think about today's class or lecture, just 1 second. So if you took I was walking around back and forth all the time, give the lecture. If the movie can be compressed in 1 second, and you're gonna take every state I possibly adopt on the stage and average out, and this would be one on me, right? And that will be very represented. It's important because this represents all the possible state that I took, and better describe me because that's more representative than I'm doing something here because that's low possible state. But doesn't mean I wouldn't do this. It's possible, right? It's just a chance of finding me standing way back here is very low because I normally don't go there. Okay? Similar, so today's lecture is more about for a given state, what do you see end-to-end distance? Because what we previously talked about is always average end-to-end distance. So h squared will be always mb squared. So it's always going to be this value. So let's say if we take mb squared root of mb squared, this would be the average end-to-end distance distribution of your polymer chain. But at any given moment, it could be smaller or it could be bigger. Like I talked about at the beginning of the class, I asked you guys what the chance of end-to-end distance. hb squared equals to 10 times mb squared. Right? It's low. 10 times mb squared is sometimes in here. You are possible to reach that state, but the possibility is very low. Okay?
So is that drawing in 3 dimension, is the origin the center of mass, or is that the start of the polymer chain?
Start of polymer chain. Yeah, we haven't talked about anything about mass center.
Okay.
Radius gyration is only discussed in that particular lecture.
Okay, cool.
So, everybody get this part? All right, so we're just going to talk quickly about one more thing. Now, we all know what's the probability distribution, right? So, if we actually just integrate and take an average of what is h squared, you could take an integration of average about h squared multiplied by probability of finding a polymer chain. I'm only going to write it out for you. It's already discussed in textbook, so you don't need to really copy the equation out. If you are curious how to do this integration, send me an email. I'm happy to walk you through in 10 minutes. Not too bad, actually, because this is integration of 0 to infinity h 4 times dh is a known function. You can actually look it up. exp minus, because we also have exponent here. This you need to require for help, because even I cannot do this integration of h squared as well as at the h squared here. This is very hard to do. Okay? Integrate h4 squared is easier, but you have an exponent of h squared. This is terrible. But if you do the math, this should be exactly mb squared, what we have talked about the whole day. Okay? Although it looks very complicated, but effectively you have two ways to understand your chain conformation. You can think about going to, I'm trying to think about a better example. You can think about going to maybe the pain center. We have two routes. You can go the left way or right way. You're both going to end there. So historically, there's two different approaches people to understand what is the average end-to-end distance. What we have talked about at the very beginning is one of the part of the scientists. They took a vector approach and used vector to understand what is the possibility of end-to-end distance. And the second half of the scientists, they don't like vector. They only like probability. They use the probability to calculate what's the probability of you finding a chain at a given distance from the center. Then they can take an average and integrate all the possibility, and you would get exactly the same conclusion. Okay? Yeah?
What is the difference if we give certain distance h and the probability you find your another end-to-end, another n, or you find the polymer sigma?
So that's a good question. So for now, we never talk about in melt states or in solution. So our discussion is strictly confined to a single polymer chain. Okay, for now. Then we will discuss the polymer solution. There is some part is talking about polymer interaction. All right?
Oh no, I'm asking the possibility you find the sigma, polymer sigma, can give you sort of idea how large the size it is. Is that right?
I didn't understand what you mean by sigma.
Because we have like two kind of possibilities. One possibility you find the other end of the polymer chain.
No, it's the same. So the difference between these two is, so if we just consider the chain end possibility, where the chain end would end up, that's the P we strictly discuss. So we don't care anything in between. So if I have to reproduce that particular curve again, so you have this random, this is talk about just the one. All the rest of polymer chain is invisible. What's the probability you find the chain end with distance h? The probability you find this particular bright dot on the scale bar is highest at the center. Okay?
So what about
This is talk about what's the chance of you find the polymer. It doesn't matter if it's from here or here, just the polymer itself. Then,
So in that cases, we simplify the polymer to a dot or to a surface or to a certain area to make that possibility calculation.
so you talk about this, right?
Right.
So in this case, we basically calculate what's the distance from the center in this case, we not only consider one dot, but any polymer chain in the equal distance to the center. Because the distance to the center, let's say for any distance r, if you draw a circle or sphere, you would intercept different part of the polymer chain. And we should consider all of these in terms of probability. Everybody following this part? What's the difference? Because this is important for you to understand chain versus the home chain. Or the other way I can give is think everybody is now a polymer chain. You are different carbon bond are in the origin. So in the second curve, it's just talk about me and Alex probability. If you take random walk, you just guys holding hand and random walk around, the chances of Alex will end up closer to me is highest. Okay? The chances that Alex was very far away from me would be the lowest, because that's defined by the random walk. And we did a long example here. If you take n step backwards and forwards, eventually you would, as n step goes up, you're still going to be ended up where you starting off. Okay? And secondly, this probability is talk about now all the distance. If I am 1 feet away, 2 feet away, how many chances I can see you? All the students, not just Alex. Okay? Now the chances is you're gonna at closer, I only gonna have 2 students, and if it's going away, because my 4 pi r square is like the spherical phase will increase, I have much better chance to find a student. So I won't pull everybody out from the details. So the summary of today's lecture, go back to the textbook to read it one more time, will help you understand, is discuss probability distribution of chain n, and chain n as well as polymer chain. Okay, if you have any question related to that particular part of the textbook, just let me know. Okay, now use the next 10 minutes. I strictly only have 10 minutes left. I'll talk about 6.6 and 6.8. 2 sections in 10 minutes. So what about now? 6.6 chapter section is talk about rods, coils, and globulars. Think about everything if we draw back in terms of, now look at the average again. H will be proportional to, or we can just use equal for now. That's what we have learned in terms of average, right? So one of the very famous polymer physicists in the 19th century is Gyration. There's 2 polymer physicists that got Nobel Prize. One is Paul Flory. We're going to learn chi parameter just in the October. The whole October is dedicated for him, so I wouldn't talk to him too much. But Gyration is another very famous French gentleman who got Nobel Prize about scale concept. We wouldn't have time to talk too much detail, but he simplified the polymer physics to understand everything in terms of scale concept. So what does scale concept? What this tells you about? The scale, in particular, is something talk about what is the relationship between one parameter versus the other. So if we think about these two, if I don't care about B, I can just abstractly think my polymer chain and the end distance average will be proportional to n power of 0.5. We only cares how does polymer scale with molecular weight. Because for a given polymer, our B is fixed. If you throw polystyrene in different solvents, your B doesn't change. But what changes is how it depends on this. For all the model, free joint chain, free rotation chain, and hinder rotation chain, H is always going to be proportional to n 0.5. Any question for that? Okay, so now if you have more rigid chain, it will change. How does end-to-end distance, let's say for rigid rod, let's use this as an example. How would it be end-to-end distance dependent on degree of polymerization? Is this the same?
Proportional to n.
It's proportional to n. Think it one more time. If it's rigid rod, your end-to-end distance is just going to be counting how many bonds, because it's rigid rod, right? We can generalize, say, this is V, okay? And V would be give you different dimensions about your polymer information. How about in bad solvent? Or when you have compact or dense polymers, globular states where we talk about everything is very compact. How does H with a scale with N? Globular state.
Does it not have an impact?
It has an impact. Maybe Lena can help us because he is reading the book. It's right there. Have you came across number?
For the globule?
Yeah, globule.
It says V is 1/3.
Why? The question is why?
Oh, sorry.
Anyone? I need a volunteer.
It's like our sphere,
Yes,
and so that's based on.
good point. So, if you think about everything is condensed as a solid sphere in a globular states, then how your end-to-end distance or size of your globular will increase as a volume, right? End distance or how big your globular is basically how does the volume of your ball increase volume is equals to V for a sphere would be right. And we know the number is proportional to the volume. R is proportional to, in this case, how big your globular state. So now we compare three very interesting states for our given polymer chain. Now you have a different dependence on the dimension, different dependence on the n. This shows strongest dependence for rigid rods. Like we talked about at the beginning, if you think about a polyethylene with 280K, you would have ended up with the longest dimension because it scales with n power of 1. It has most dependence on the length. In any ideal chain cases, your end-to-end distance increase with n 0.5. We always call this as a phantom chain or free joint chain or any chain, but in other words, this would be the ideal chain in three-dimensional space. And if it's really compact, this has lowest dependence, or when you molecular increases, this goes up most slowly, right? This scale basically tells you how rapid your end-to-end distance will depend on the n. So scaling in concept is very helpful for you to understand what is the quality of your polymer chain in different solvent. Because this is something we haven't discussed, and I think I'm just about over the time. So I'll keep the 6.8 real chains as the next class, okay? So in the next class, we're going to cover the last chapter, and we're also going to talk about the homeworks. Okay, so today is also due for the first part from 4 to 7 or 4 to 8 into 4 to 7. Okay. So in the real chain, we're going to discuss next 10 minutes in the last class. And anybody want to guess what would be real chain's dependence in terms of this? How does real chain in terms of end-to-end distance depend on n? It's going to be 0.5? No? I see some of you shaking your heads. Why? Why it wouldn't be for the real polymer chain has end-to-end distance depends on n as power of 0.5. That's a key question. I want you guys to walk out the classroom and know this answer. Okay, for the next class, I can give you a hint. I want to have a vote. Do you think it will have a stronger dependence on n for real chain or lower? In other words, for real chain, will be V larger than 0.5 or smaller than 0.5. We talked about if it's smaller than 0.5, it's in globular states. If it's larger than 0.5, it's more closer to rigid rod chain. All right, who think it will be lower?
It will be lower.
1, 2, 3. Okay, who think it will be higher? You have to vote. Okay, majority class thinks it will be higher. We will see in the next class. Okay? Because that tells you the solvent quality. Homework, just to leave it here.